This is the lecturette for section 17.1 and 2. The first part, 17.1, involves acid-base reactions and looking at their equilibria, and the second part involves buffer solutions. So acid-base reactions, you know from studying net ionic equations quite a few chapters ago. And the idea here is to try to predict the reaction for different combinations of strong and or weak acids and bases. And we want to do two things. We want to define the extent of the reaction, that is, how far do those reactions go to completion. And secondly, we want to talk about what the acid-base properties of the products will be. So the first thing we do is look at just some examples of the degree of reaction that happens. When an acid-base reaction happens between a strong acid and a strong base, like HCl and NaOH, it makes water and a pH-neutral salt, and that goes to 100%. If HCl, a strong acid, reacts with a weak base, NH3, that goes to make ammonium ion and chloride ion, and that also goes to 100%. If a weak acid, however, reacts with a weak base, in this case HF, which is a relatively strong but still within the categories of weak acids, and acetate ion react, makes acetic acid and fluoride ion, that goes less than 100%. That goes about a little less than 90, between 90 and 100%. And if you take HCN and ammonia and react those, a weak acid and weak base, that only goes around about 50%, 45-50%. Let's look for a second about the acid-base properties of the resulting solutions. If you have a strong acid and a strong base, you make water and a pH-neutral salt. pH-neutral in that the sodium ion is neither acidic nor basic, and the chloride ion is neither acidic nor basic. So that makes a neutral solution. So that solution would have a pH of about 7. If you react a strong acid with a weak base, you make a weak acid, that is ammonium ion is a weak acid, and a pH-neutral anion. And so that solution will be acidic. And so the pH will be less than 7. If you, not shown here, react a weak acid with a strong base, something, for example, like HNO2 plus sodium hydroxide, you go to make, that goes 100% as well, that goes to make sodium nitrite plus water. And the sodium nitrite contains nitrite ion, which is a weak base, and so therefore the solution there would be basic, because you have that weak base in solution, and the pH would be above 7. When you have acids and bases that are both weak and occur, the acid-base properties of the resulting solution will depend on the relative strength of the weak acid and the weak base. So let's talk about extent of reaction in a little more detail. So if a strong acid and a strong base react, the reaction goes to 100%. If a strong acid and a weak base react, it goes 100%. If a weak acid and a strong base react, it goes 100%. That means that all acid-base reactions involve either a strong acid or a strong base go 100%. If a weak acid and a weak base react, the extent will depend on the acid and base strengths, and that's what we'll look at next. So there's a table of 7 different reactions between weak acids and weak bases. In the first part here, we're going to hold the base constant. We're going to use ammonia, so the base isn't changing. And we're going to look at the extent of the reaction. So if HF reacts with ammonia, the reaction will go about 99%. And these are all based on around 0.1 molar solutions reacting. It changes a bit if you have different concentrations. If you go from HF to carbonic acid to HCN, what happens is as the acid gets weaker, the extent of the reaction gets smaller. So as you go from HF to H2CO3, the Ka goes down by about 1,000, and the extent of reaction becomes less. As you go from carbonic acid to HCN, that is, the Ka decreases about another 1,000, and the extent of reaction goes down significantly further. So the weaker the weak acid, the less the reaction goes. Now let's look at the effective bases. So if we hold our acids constant, and we look at 3 different bases in decreasing order of base strength, so we go from ammonia to acetate ion to nitrite ion, as the base gets weaker, as you can see from the decreasing Kb values, the extent of reaction gets smaller. So what we see is the stronger the acid and the stronger the base, the greater the extent of the reaction. So the acid and the base independently lead to greater extent of reaction the stronger either of them are. That means if you have a reaction between a very weak base and a very weak acid, it shouldn't go very far. And this last example shows that. HCN is a very weak acid. Ka is around 10 to the minus 10. Nitrite ion is a very weak base. Its Kb is around 10 to the minus 11, and it only goes to an extent of around 0.1%. You can quantify this a bit by determining the K value, the equilibrium constant for acid-base reactions. If you have a strong acid and a strong base, like HCl reacting with NaOH, the full ionic equation is written here, and the net ionic equation is a hydronium ion plus a hydroxide ion goes to make 2 waters. And that's the opposite, this opposite reaction of the water ionization, self-ionization reaction. So therefore, because it's the reverse of that, the K value for this is 1 over Kw, because Kw would be the reaction, the equilibrium constant for 2 waters going to make hydronium and hydroxide. Because we have the reverse of that, it's 1 over Kw, so that reaction has a K value of 10 to the 14th, the positive 14th. So it's very highly favored. The reaction essentially goes completion to the products. If we now look at a typical strong acid, weak base reaction, we'll look at HCl reacting with ammonia. If you do the net equation for that, it's hydronium ion reacts with ammonia to make water and ammonium ion. When that happens, if you notice, this reaction is the reverse of the Ka equation, Ka reaction. The reaction defines the Ka of ammonium ion. So therefore, because it's the reverse reaction from the ammonium ionization reaction with water, the K for this reaction is 1 over the Ka. So if we substitute in the Ka for ammonium ion, 1 over that, we come up with a K for this reaction of 1.8 times 10 to the 9th. Again, a very large value, and the reaction will go to completion. If we look at another example, a weak acid and a strong base, we have hydroxide reacting with hypochlorous acid. That goes to make hypochlorite ion and water. This is the reverse reaction of the Kb reaction for this weak base. And therefore, K for this is 1 over the Kb for the weak base. We substitute that in from the table of Kb's. We end up again with a very large value. The reaction again goes 100%. So that's the more quantitative explanation for why any reaction involving a strong acid or a strong base, or both, goes to completion, or very nearly so. If you have a reaction between a weak acid and a weak base, you have to do a little more work to figure out the equilibrium constant for it. If you have hypochlorous acid and ammonia reacting, you can write down the reaction for that first reaction, and that is the Ka reaction for hypochlorous acid reacting with water, and that Ka value is from the Ka table. Then you have ammonia reacting with water, goes to make ammonium ion and hydroxide, and that's the Kb reaction, and so you can write down its Kb. If you then take the water, the reverse of the water self-ionization reaction, as hydronium reacting with hydroxide to make 2 waters, the K for that, as we saw before, is 10 to the 14th. And if you add all these up, you get the reaction that we're interested in here. So our goal is to find the reaction for this net reaction. If you add these up, these three reactions up in the way we have, you end up with the reaction that you're interested in. That's the reaction we care about. So when you add up these 3 reactions, you have to add up you have to take the product of the 3 different K values. So it's going to be Ka times Kb times 1 over Kw. When you do that out, you get 63, which means that this reaction lies to the right, but it does not. So its percent of that it will go is greater than, say, 50%, but it's not very, very strongly over to the right. So by no means goes 100%. So that ends section 17.1. Now we're going to turn to section 17.2, where we examine buffer solutions. The idea of a buffer solution is that a buffer solution contains a mixture of bulk quantities of a weak acid and a weak base. They both have to be present in significant concentration. Typically, this works by having a conjugate acid-base pair, so a weak acid and its conjugate base. The important property of a buffer solution is that it experiences a relatively small change in pH if you perturb it by adding a strong acid or a strong base. And so what we're going to do is we're going to look at identifying buffers. We're going to look at figuring out how to determine the buffer pH. And we're going to look at changes in buffer pH when acids or bases are added to the buffer. And finally, we'll look at how to prepare buffer solutions, which is one of the more useful, practical things that you'll learn in this probably entire course. Okay, how a buffer works from a chemical point of view is that if a strong, remember, a buffer exists as a weak acid, it's a solution of a weak acid, plus a weak base. And the idea is either of those could react if things that they react with are added to the solution. So what happens is if a strong acid is added to the buffer, that acid that you add is going to react with the weak base of that pair, because they're both present. On the other hand, if a strong base is added to the buffer solution, it will react with the weak acid that's there. So basically what you're doing is you're preparing a solution that has components that will react with either a weak acid or a weak base that get added to the solution. So let's look at this with reaction equations. Let's say we made a solution up of acetic acid and sodium acetate. The sodium acetate is a salt. It's soluble, so it breaks up into two ions, and the ion we care about is the acetate ion, which is our weak base, and the acetic acid is our weak acid. So if HCl is added to the solution, it makes a hydronium ion by reacting with water, and that hydronium ion, instead of simply lowering the pH, will instead react with the acetate ion to make acetic acid. So what you're doing is, by having the acetate ion there, you're consuming the H3O plus and taking that strong acid and instead making it into a weak acid. So the solution will become somewhat more acidic, but much less so than it would have otherwise. In addition, in a similar way, if hydroxide is added to the solution, it will react with weak acid. And so the hydroxide is added to the solution, it reacts with acetic acid. That then makes water and acetate ion. So you're taking the strong base, it's consumed, and you're making a weak base out of it. So if you add hydroxide to the solution will become a little more basic, but not nearly as much as if the buffer was not there. Okay, the next thing we're going to look at is what happens when you add a strong acid or base to a buffer solution. How does that change the pH? By how much? So we're going to look at an example using a strong base. So the key is, what you want to do is you want to use the Henderson-Hasselbalch equation to determine the pH before anything happens. You could use an ice table as well. It gets you to the same place. Then we're going to add the strong base and assume that the strong base reacts completely with the weak acid. And the key here is what will happen is the weak acid will be converted into weak base. That is, the hydroxide will convert the weak acid into weak base. So the weak acid concentration will decrease, the weak base concentration will increase. And then we'll determine the final concentration of those two after reaction and use those concentrations with the Henderson-Hasselbalch equation to determine the new pH and then take the difference between them. So our specific example is going to ask, what's the pH change when 16 milliliters of 2.5 molar NaOH is added to 500 milliliters of a solution containing 0.32 molar ammonium bromide and 0.46 molar ammonia? What we'll care about here is that it's ammonium ion. So our first task is to determine the pH. The pH is going to equal the pKa, which we saw earlier on was 9.25, plus the log of the base over the acid concentration. In this case, the base is the ammonia, so it's 0.46, divided by the acid concentration, which is 0.32. Do that, come out with 9.41. So that's our initial pH. That's the easy part. The next part is to assume that the acid, the weak acid, is going to be consumed by the strong base and converted into weak base. So what's going to happen is ammonium ion is going to react with hydroxide ion to make water, which we don't care about, and ammonia. And what we want to do is we want to make an amounts table, which is like an ice table, but for a reaction that goes 100%. So we're going to have initial amounts, change, and final. We want to do this in terms of the amounts of those species in moles. So we have to determine the moles that are there. So we have 0.500 liters times 0.32 moles of NH4 plus per liter. So that's 0.16 moles of NH4 plus. We have 0.500 liters times 0.46 moles of NH3 per 1 liter. So that gives 0.23 moles of NH3. The hydroxide is 0.016 liters times 2.5 moles of hydroxide per liter. That comes out to be 0.040 moles of hydroxide. So we insert these in here. So it's 0.16 moles of ammonium ion, 0.040 moles of hydroxide, water we don't care about, 0.23 moles of ammonia. So of our two reactants, the hydroxide is the limiting reactant, so it's going to control how much reacts. So it's going to be minus 0.04 moles of that. That will consume 0.04 moles of our ammonium, leaving us with 0.12 moles of ammonium, 0 hydroxide. But when the hydroxide reacts with the ammonium, it creates more ammonia. So we're going to add 0.04 moles of ammonia. So we're going to put 0.27 moles of ammonia. So next what we want to do is we want to determine the concentrations of the ammonium and the ammonia, and then use those to determine the new pH. So I'm going to go to a blank screen. We now have 0.12 moles of ammonium, and we have 0.27 moles of ammonia. And notice that we had 500 milliliters, and we added 16 milliliters to that. So we're going to divide this by 0.516 liters, and this by 0.516 liters to get the new concentrations of each of those. So if we take 0.12 and divide it by 0.516, we get 0.233 moles per liter for our ammonium ion. If we take 0.27 and divide it by 0.516, that's the combined, volume, we get 0.523 molar. So now we can determine our new pH. pH equals the pKa 9.25 plus the log of our base concentration, which is 0.523, over our acid concentration, 0.233. That gives 9.60. So it makes sense that the pH went up because we added a base to the solution. So the change in pH is equal to 9.60 minus our initial pH, which was 9.41, which is an increase of plus 0.19. One thing to note is when we did our calculation of figuring out the concentrations of these two to take that ratio, because the volumes are the same, this equation, the Henderson-Hasselbalch equation, will work the same way if you just use amounts in moles here. So if we did the same thing using pH equals the pKa 9.25 plus the log of the relative number of moles of the two as opposed to their concentrations, it would have worked the same way. If we had 0.27 moles of ammonia over 0.12 moles of ammonium, you still come up with 9.60. So that saves a little bit of a step along the way. Okay, the next thing we want to turn to, our last portion of these two sections, is how do you actually make a buffer if you want to know, if you want to make a buffer of a particular pH. There's two ways to do it. One is by simply adding known amounts that you've determined ahead of time of weak acid and weak base together and make a buffer by doing that. The second way is to take either a weak base or a weak acid solution and add a strong base or acid to it to convert some but not all of the weak to its conjugate till you get the right ratio. So in order to do this, the process is the same for our first two steps, and then we change in how we go about it by our two different methods. So first thing, what you want to do is you need to choose an acid-base pair with a pKa near the desired pH. So remember, for all buffers, pH is near the pKa of the weak acid of the acid-base conjugate pair. And so you need to pick an acid-base pair that's close to has a pKa close to the pH you want. Then what you do is you determine the ratio of the acid to the base needed. That is the specific ratio of the weak acid to weak base you need for your particular pH that you desire. Then you either determine the masses of the acid and base to use, the weak acid and the weak base to use, or you determine the volumes of your acid and base solutions to mix to get what you want. So we're going to do an example of each of these. We're going to do direct addition first and preparation by acid-base reaction second. Okay, so let's say we want to make 250 milliliters of a buffer that has a pH of 4.32. And we want our weak acid concentration of the buffer to be 0.5 molar. We have these three different acids here and three different acid-base conjugate pairs. First thing we have to do is we have to choose which of these three to use. And the idea is the pKa's need to be near, the pKa needs to be near the pH we want. And of these three, clearly the acetic acid acetate acid-base pair has a pKa that's close to the pH we want. So that's the first thing to do. The next thing to do is to determine the ratio of acid to base that we want. That is the ratio of acetic acid to acetate we're going to need. And so we're going to use the fact that we saw before, that H3O plus concentration for a buffer is equal to the Ka times the concentration of the weak acid over the concentration of the weak base. Because we know the pH we want, we can know the H3O plus concentration. So that's going to be equal to 10 to the minus pH, so minus 4.32. So we take 10 to the minus 4.32, and we get 4.79 times 10 to the minus 5. That's going to equal the Ka for acetic acid, 1.8 times 10 to the minus 5, times the ratio of acid to base. And we're looking for the ratio of acid to base, so what we'll do is we will actually write in formulas now. CH3CO2H, that's our weak acid. CH3CO2 minus, that's our base. That's going to equal 4.79 times 10 to the minus 5 divided by 1.8 times 10 to the minus 5. If you divide those, you get 2.66, which means our buffer needs 2.66 times as much acetic acid as acetate, which makes sense because the pH is lower than the pKa, which means that you need to add some more acid to get it a bit more acidic. Okay. Then what we have to do is we have to determine the amounts that we're going to want. So the next thing is say we know we want our acetic acid to be 0.5 molar, and we want to make 0.25 liters of that. So we're going to take 0.250. So we're going to take 0.250 liters times 0.500 moles of CH3CO2H per liter times the molar mass for acetic acid, which is 60.05 grams per mole. And then that tells us the mass of acetic acid we want to use. We want to use 7.51 grams of acetic acid. Now, the amount of, so we know how much acetic acid we want to use. We'll turn now to the acetate. And so the key for the acetate is that we know that the acetate needs to be the acid needs to be 2.66 times as strong as the acetate. So the acetate concentration is going to equal the concentration of our acid divided by 2.66, because the acid needs to be 2.66 greater. So that comes out to 0.188 molar of our base. And so now for the base, what I'm going to do is I'm going to, instead of using just acetate, I'm going to use sodium acetate, because you can't have a mass of just ions. You have to have a compound you're going to weigh out in the lab. So now what we're going to do is we're going to take 250 milliliters, 0.25 liters, times 0.188 moles of, in this case, sodium acetate per liter, times the molar mass for sodium acetate, which is 82.03 grams of sodium acetate per mole. And that gives us our mass of sodium acetate, and it comes out to 3.86 grams of sodium acetate. And so the idea is, if you use a volumetric flask and add some water to it, and then add 7.51 grams of acetic acid and 3.86 grams of sodium acetate, you will in fact arrive at a buffer of 4.32. We turn now to our final example, where we prepare a buffer by using an acid-base reaction. In this case, we want to know what volume of 2 molar NaOH solution should be used to be added to a 250 milliliters solution of 0.5 molar acetic acid to create a buffer of 4.32 pH, which is the same pH we had a moment ago. And the idea here is that, again, what we want to have is we want to end up with a solution that has a mixture of acetate and acetic acid that will lead to this pH. And so, like we saw before, the H3O plus concentration is going to equal 10 to the minus 4.32, which is going to equal 4.79 times 10 to the minus 5 molar. And so the concentration of acetic acid to acetate ion is going to equal the H3O plus concentration divided by the Ka, which, as we saw before, for the same pH buffer is 2.66. That means we want to have 2.66 more acetic acid in our buffer than acetate. And the idea here is, what we're going to do is we're going to start with a bunch of acetic acid, and we're going to add NaOH, and the hydroxide is going to convert some of that to acetate. And the idea is we want to diminish our amount of acetic acid, increase our amount of acetate until we reach that ratio. And so our goal is to say, how much of this must we turn into that to get to that ratio there? And so what we're going to do is we're going to start out by talking about how many moles of acetic acid we have, and then go from there. So our initial amount of acetic acid is 0.250 liters times 0.500 moles of acetic acid per liter. And so that means we have 0.125 moles of acetic acid. When the reaction happens, for each mole of hydroxide that we use from our sodium hydroxide, we're going to decrease our amount of acetic acid by X. And we're going to increase our amount of acetate by X. And so X is the amount of hydroxide we're going to add. So therefore, we know that what we want our CH3CO2H divided by our acetate to be equal to 2.66. And we know that X is the amount of hydroxide we're going to be adding in, of sodium hydroxide we're going to be adding in. And we know that this is going to be 0.125 minus X, and this is going to be X. So then we have to solve for x. So 2.66x equals 0.125 minus x. So therefore 3.66x equals 0.125. X equals 0.125 divided by 3.66, and that equals 0.34. 0.034 moles of sodium hydroxide. So that's how many moles of sodium hydroxide we need to add to convert acetic acid into acetate ion to get to that ratio that we want. We then use our concentration of sodium hydroxide solution to figure out what volume that would be. So it's 0.034 moles of NaOH times 1 liter for every 2 moles. So that comes out to 0.017 liters, which means 17 milliliters. So what you would do to create this solution is you would take 250 milliliters of 0.5 molar acetic acid and add exactly 17 milliliters of exactly 2 molar NaOH, and then that solution will have the correct pH of 4.32.